And welcome back. We continue with the Helmholtz principle. Okay, so this question reads: a car mass 960 kilograms has a constant tractive resistance, once again, of 350 newtons. Is driven on a slope of 1 in 12. Right? Determine the following: the force required to send the car up the slope at 2 meters per second squared, and the power developed at the wheels. So there's a bit of new old concepts. When the speed is 90 kilometers per hour. The force required to retard the car down the slope at 7 meters per second squared, and the brake power developed right at that instant. So of course it's a instantaneous speed at a particular one. How much power to brake the vehicle at that time? So the first things first, we have to draw a vehicle. So we'll draw him over here. We'll draw it rather. So we can have it like this maybe. Okay. So what we're having here is a car coming up a slope here, right? And we are looking for the force required to get that car up, basically. So you can call it Fe again. I'm just borrowing on the previous example so you can just kind of get a feel for this. And I'm incorporating the incline component of the previous one. All right. And of course, as it's going up, we've got the tractive resistance, Fr. We've got the inertial resistance, Fz, the inertial force. And also on the slope, we've got another force. So of course we have our infamous, our component of our weight is split over here. That's going to be your mg cos. And you've got, I'm just writing in green so you can see mg sine theta. You get the idea, right? And it's accelerating up 2 meters per second. So it's fairly simple. Again, we've got to generate the force balance as before. I hope it's going to be simple. So you know that force some of the force in the x direction, right, will be Fe, and I'll just say equal here, Fz plus Fr plus mg sine theta. Right, simple. Right. Once we have this, I think we can actually solve this. We've got all the numbers. Fz is the mass, 960 kilograms. We've got the acceleration, that's 2. We've got Fr, which is the tractive resistance, is 350 newtons total, and then we've got the mg sine. So that's the time here we go, 960 times 9.81. So they've given the mass now, and then we can times that by 1 over 12. So I hope you guys are aware of you're allowed to do something like that. I'm not sure if everyone is familiar with mg sine and 1 over 12 and all of that. Right. Then I think there's no frictional force because it's included in the tractive resistance. So we add this, we'll get that force. Let's just quickly see. Times 1 over times 2 is acceleration. That's 350 plus 960 times 9.81 times 1 over 12. What answer do you get? I'm just making sure my answers are correct here. What is your tractive effort? The force required to lift the vehicle up? What did you guys get?
3054.8.
Okay, 3054.8. That looks proper. So the solver, they've also required us to find the power. Do you know the relationship for power? What is power equal to in a translational or linear form? Are you aware of it? Do you remember?
Force time velocity, sir.
Fantastic. So we take 3054.8. Of course, they're assuming, this is at the instant. So it's not accelerating. So at a particular time. So of course, that's going to be 90 divided by 3.6. So what we mean here is that there's how much power is required to get this vehicle up here. So if you had some kind of engine, for instance, I mean, most cars could easily go up to, depending on what you're looking at. So let's look at a basic concept, let me go for Polo Vivo here. Let's show you as a quick way of one way to view it, possibly. Just gonna cut out something for you and paste it. While I'm thinking, engine. So, okay, so got it. Yeah. So I'm not gonna want to screenshot the whole thing though. But if you go on cars.co.za, for instance, you look at, just zoom it up. It's a normal Polo Vivo. It's a 1.4 engine capacity, a 4-cylinder. So the power max around 55 kilowatts. This car is particularly quite strange. You need, would you think that this car would be able to go up this incline, given the specs of the? What do you guys think? So it's rated at 50. Its maximum power is 55 kilowatts, and in our case, when the speed is at 90, we need around that much power. So arguably, I think that this car is unable to climb up that slope, because I mean, we get the max power, so we needed that amount of power. So this example doesn't seem quite well. It's not. I would say it's practical, but it depends on the size of the vehicle. This is the way I understand my analysis. And if you look at I'm looking at now, maybe the weight. It's the engine general. Doesn't really tell me the weight. Specs. It weighs around 1,000. It weighs around a ton. So I'm not sure if I'm interpreting that correct, but that's how much power we need at that speed anyway, of course. So yeah, okay, I'm happy with that. The next thing he says, the force required to retard the car down the slope. So now we've got another situation here. You can probably write it below. So always, mechanics, you're going to need to do your free body diagram. It is of utmost importance. Right. And we have the same forces acting, but now they want to know how much power we need to stop it. Stop that car when it's traveling at 108. So what happens, kilometers per hour? So what happens here? The forces now, your inertial force is at the back. Is it not so? Or where's our inertial force actually? So you've got a tractor force here. And we've got mg sine. So there's now an interesting problem before I get too excited. Let me just get up mg sine green again, because now it's an interesting case before I get too excited. mg sine. Okay, so if you read up, it says the force required to retard the car down the slope at 7 meters per second squared, right? And the brake power developed at that instant when the speed is 108. So our forces don't change in this case, because we're assuming that it was the same kind of car, well, the same conditions over here, right? But then I feel a bit strange with the way to phrase the question. They should phrase it a lot differently. The the force required to retard, because we're essentially braking, so therefore it has to act in the other way. So the car has to move forward. Oh, they're just kind of saying so then in this case it follows the same kind of thing. And now all our forces basically remain exactly in the same place essentially. And there's nothing has really changed over here. So I'm not really particularly happy with the way they worded this problem, because out of put my force on the other side here. The frictional force, where was our frictional force? Should have not. So we have a tractor force going this way. Strange enough, right? And then our force of the vehicle would be the actual force. But let me, before I follow that train of thought, I would rather prefer, let me do it the way I perceive it first, because this way is a bit suspicious to me. Okay, so let me just sketch this down here. Are you guys all with me with the question? Like the reason why I'm finding it weird in terms of the forces? So just quickly do it the way I perceive. So tractor force this way, we've got FZ going that way. You've got an actual force going forward, and we have mg sine. So I'm just going to do it this way. From the way I understand, because I mean it's going down, so the forces have to change. I think I know exactly why they've decided the same slope. So what we do here, so I'm just going to say MS, that's my approach. Unless I'm reading the question wrong first, and then we will check if the approaches line up within the example itself. So we have F, E, the tractive effort, plus mg sine. All right. And that'll be equal to Fz plus your tractive resistance. This is what I envision the problem to look like, because it's going down. Tractive resistance has to be the other way, and of course you're fighting, you're still resisting the inertia. You still have to beat inertia, which has to go other way. So I'm not particularly sure exactly how they. So this is Fe. I hope I get the same answer though, but if I don't, that's going to be a bit of a problem. Hopefully we can all figure that out. That's minus mg sine. So if you have a look at this, it's exactly the same thing, but we're just subtracting this piece over here. So that's 960 times 2 plus 350. That's minus 960 times 9,81 times 1 over 12. So like I said, this is my approach. Let's have a look what we get. One over 12. So I get 1,485.2 newtons. So in the book, they have a different braking force. Oh, sorry, my mistake. Of course, my FZ has to change. So this is 960 times 7. Forgive me for this. Let's just quickly have a look. I have to adjust my. So I'm just doing it based on the way I interpret this question. At least I have some funny wordplay which I'm not getting. And I instead get. Can you guys just check my answer? You guys agree? 6,285.2 newtons.
Okay, I got the same. Yeah.
Yeah. So I'm not exactly sure. The force they get here is 7,155 newtons. Now, I'm just not too sure exactly how that will work out here. But I think it's to do with the way the body is accelerating, because it's decelerating, and I'm not too sure. I have to really, but I get that value and the power required, 685.2 times. So in new speed now though, and the speed is at 108. So maybe I'm not understand the question properly. I'll just refer back to it now. Times 1/8 divided by 3.6. And I get 188.56 kilowatts. So this is our guess, our approach. But I think what we're looking at over here is, so if you look at the previous one, right? The velocity is going this way, right? And the body is accelerating in the same direction, right? So it's normally 2 arrows for that. So in that case, we can apply that. Now in this case, the velocity is going forward, right? And I think that the reason why it's changing, and I figured out actually why, and this is the reason why. So we're going forward, but we have to decelerate, right? If it makes sense. So remember that inertial force, like if you remember the truck, the truck hitting you, the truck, in the case where the truck, with the rock came out of the truck, the picture showed you. And in this case, the acceleration is going the other way. So of course, the elements principle talks about the acceleration of the object. And so if it's going that way, if the acceleration is going this way, the inertial force should be going that way, because we're decelerating. I hope you all got that. So can you see in this approach, it doesn't work the way we think it works. So this is actually wrong. So it has to do with the acceleration of the object. Did we all get that? Because that's a bit tricky. That's why I'm doing
Yes,
this.
sir. I get it. I get it.
So to do with acceleration, because if you think about it, the inertial force, if we were braking, right, we're going to get a force pushing this way. So let's say we're driving and we apply brakes, dead brakes, as one says, and then we kind of move. But we move forward, we go back, forward, you're going to feel that force. But instantly, I think you'd feel it the other way, but then you'd feel it coming backwards. Not that way, man. I'm saying the whole way. Yeah. So in this case, we're going to do the balance like that. So be careful of the way the bodies are. If it's coming down and it's in this case, it was decelerating. That's why it's going this way. But it was accelerating, it would have been exactly this way. So it was accelerating. So this is the case. If you were accelerating, if you were driving forward, I'll say the acceleration is this way. Forward. It's not writing now. So it's not incorrect. Just that. Okay, just bear with me, guys. My pen is just not listening to me now. Yes.
So does that mean that now we do the calculation exactly the same, but we'll put the acceleration as negative?
Tammy, do you think that's well, maybe that's no. So we have to. Our forces
So
will
I
change
did that, but it obviously spits out a negative force.
On this side here.
Yeah.
I don't know why I can't. Yeah, so now what I'm saying is you have to go back to the initial diagram we drawn over here. This is like the first approach which I thought, but then so also we have to go back to B. This I just can't write for some reason. Yeah. Just trying to figure out what's happening with my pen here. Just a second. So if just open my PowerPoint and have a look. It's writing there. Oh, maybe it says Skype. Figure out exactly what's going on. So what I'm saying is we've got to use this, the first diagram I drew. Oh. Hello. I see you, but it's not obeying me. Guys, just give me a second. So you guys can try in the meantime. So we're splitting a force. So what I'm just saying is that on this side, we're assuming that the body was accelerating. Oh, there we go. Thank you. If we were going forward, the velocity is going forward, of course, but then we're accelerating forwards. In this case, we are not accelerating forwards. We are decelerating. So if we are going forward and we press, but in this case, the car is slowly decreasing speed, and then we brake. In this case, We increase in speed and then we brake, which is quite strange. But anyway, so we do exactly the same thing again here. So then we're looking for FE, and FE is going to be equal to FZ plus mg sine minus F R. Yeah. So if you add these guys up, you should get a value of 7,155 newtons. And then your power in this case is going to be 960. What's the weight again? So it's 4 times velocity, my bad. 7,555 times 108. 3.6. So it's very interesting actually to think about 214 kilowatt. So you require more power to stop a vehicle, even though it's decelerating, versus accelerating down the slope, you require less power. That's very interesting. Do you all get this? What I'm talking about? So we have to look at acceleration. Look at this vector. Look at acceleration. Look how the body is accelerating. Okay, are we happy with this? Can I move on? 14.6. This is an example in the textbook. So yeah, for your note back. Are we all good with this?
Yeah,
Is this the one
follow. Which example is
Yeah.
it? Just so I can note it down.
Example 5.
Thank you.
On page 430.
Okay.
Yeah. So okay. So make sure when you study go over all the examples. Obviously, I mean, you should know this. Okay, I'm gonna do the last one. And then we can call it for today, guys. I know this is getting back in mechanics again. All these new forces and things changing, but always have these important notes. Let's just open up the exercise quickly. Where is it? There's about 10 questions. Yeah, I highly recommend going over all those 10 questions. Yeah, that's all I'm going to say. Go over those 10 questions for the elements. All right, so last example for the day. Then I'll see you on Friday for some relative velocity. Okay. Let's just quickly get that example for you, and then we can have a break. We'll have a break. I'll see you. I need to see you. So I'm just screenshotting it quickly. I'll just move it to the side here. Okay, I think I should actually just like this. Cut it. Okay. Fantastic. Cool. So in this case, what do we have now? Last one for today. A body mass 53 kilos resting on a plane at incline at 25 degrees to the horizontal. All right. Let's just get that drawn first. Yes, it's also in the notes. It's also in the notes. All in the notes. All in the notes. There's funny handwriting here. It's all in the notes. All right. These questions will go for around they're around 10-15 marks. So make sure you bank those. Oh, okay. Okay, great. Thank you. That's example 4. 25 degrees. Perfect. Then it says it's attached to a hanging weight, mass 47 kilograms by a light inextensible cord and passes over frictionless pulley, or the classic frictionless pulley. Right. So we have some pulley over there, and we have this weight. So I'm just gonna make it look like that, so we can have So the body itself is 53 kilograms, right? This is 47 kilograms, okay? And then they say, yeah, okay, so it's situated on top of the slope as to maintain the chord parallel to it. Okay, fine. No problems there. The system is held at rest. The coefficient of friction between the 50 kilogram mass and the inclined plane. So we've got some friction on the plane itself. You know, that's static friction, one could say. U is 0.3. When it's released, so this mass is being released, right? Strangely enough, when it's released, determine the acceleration of the system and the tension in the chord. So we want to know that chord they talked about, which is joining the hanging mass and the body on the plane. What is the tension and acceleration of the system? And they're saying how much power is developed at the instant the velocity is 1.8 meters. Right, so obviously, let's just figure out what's happening. Right, this seems a lot of things happening. So we normally start on the slope. Zoom up a bit. It's a very bad drawing. And now what I'm trying to figure out here, right? So which way is acceleration? So of course we know that the tension here, I'm going to call it T1, is the same tension over here, right? If there's friction, the tension will change across here. So in this case, that's fine, right? We know we've got our mg sign. Obviously, I'm just adding all the normal stuff here, so we all know. Your mg sign is over here. You've got your cos, obviously mg. Now I'm to remove the friction. So from what I would initially thought here, and maybe this is where it's a bit tricky, reading it, is that let's just put a kilogram here so we can see. Don't wanna. 47. Hope you can see that. Okay. So now it's saying if we release the system, right? The system is held at rest, and it seems like the system is accelerating downwards here. Now, how do we discern that? How do we know? Because if we release it, I would assume the mass to pull all of this down, because I mean that is heavier than that. But in this case, what's happening is that the acceleration is going this way. Right? Okay, that means the velocity is also going this way. And that's the case, our F mu and our Fz is all over here. F mu, Fz. I would love to run this experiment with you guys to see if it's all true and well. And if we look here, this is going to go down, and then therefore our Fz is going that way as well. But in this case, we also have your mass pushing down over here. So this is mg. All right, so now we're going to set up a few equations. Now we start off with on the slope. Look at those forces there. So we have T1, and T1 is equal to a whole compendium of force. That's F mu plus mg sine theta plus Fz. Okay, do we know our normal force? Oh, we're looking for the acceleration, by the way. So that's important. So F mu is 0.3, and that's times 53 times G. I'm just going to use right G's for the sake of 9.81, easy to write. times cos of 25. Just following the book style of thought here. So G is 9, guys, we're on Earth. Well, not particularly on Earth. This is the general accepted gravity. Gravity at, let's just look at gravity at Ranger Bay, Cape Town rather. Yeah, where did I leave you guys? I just realized like after 3 minutes now that I realized that I've left. I don't know what happened. So where were we when we left? Smoke break. I'll show you how far I got here. Were you guys aware of where I was busy showing you the gravity? Do you guys see the gravity? I'm still recording, great. So I'll show you different gravitational constants. Do you guys have a look at that at least before we got cut off? So I'm not sure exactly where we left off. Mr. Abril, speak to me, man. You didn't start the question. What does that mean? The example. The actual example, I didn't start the question. Oh, okay. Mike. You're drawing the diagram. Oh, okay. I see. Okay, guys. So as you can see, I've gotten a bit. I've managed to move quite a bit there. And you know what happened there. I was drawing the diagram. Also, I was looking at all the forces basically. And what I want to show you was the gravitational constant. But then I realized, I had to look at the notes that they took G as a variable, which doesn't make sense to me. And I'm going to just have a look now quickly at something before we proceed. I just want to see if we're on the right track here. Yeah, one. Okay. Oh, let's see. I'm realizing something very strange on my end here. So one, well, not strange, but okay, it's fine. Let's see, should be. Okay, great. Anyway, I think I'm still correct, obviously. Should be fine. So guys, what I basically did is I looked at the forces on the slope. And as you can see there, the tension in the rope will be equal to F mu plus mg sine theta plus Fz. Are you guys happy with that? All I basically did at the end is added them all up, and then I ended up with I added those, and I end up with 361 plus 53 times the acceleration. Are we happy with this? That's on the slope, right? Can I get an amen there? Thank you. And then what I did, I went to the mass hanging on the rope, and what happened is that we have T1, right? And T1 is of course acting this way now, just to balance the other force on the other side. That is equal to Fz because the system is moving downwards, and that's equal to mg because that is the other force. In the end, I just basically solved solve for the mass, got that value, and I end up with T1 and A. So our two variables need to be solved. Again, a simultaneous equation, or what Brain likes, a matrix. So what I'm doing now, I'm going to be putting these values in the matrix and then solving it. So the T1, I'm solving T1, and I'm solving A. I have over here, T1 is going to be 1. That's going to be minus 0.53. This is going to be 1, and that's going to be 47. And this will be now equal to 361.097. And this is going to be, oh, this is not 0.53. What am I writing here? It's 53. Yeah, it's 53, sorry. 53 but negative. And 147 of this stage about 461. Mr. Silver, can you please use your calculator and find these values for us? So we're going to get T1 and we're going to get A. And I think that's the first part of the question. I had something there. Okay. Laugh out loud. Oh, yeah. So Mr. Keith, can we just solve that matrix quickly? That 2 by 2. So of course, guys, you need to make this in the right order. So of course, I just move that to the other side. It has to be TA, X, whatever the variables are. Call it A, whatever. A T1 plus B. Oh man, I can't be using this. But you have to make sure it's placed in T1 plus A equals whatever T1 plus A. Of course, as normal. So what values do I get for T1? And the acceleration. You guys are taking long there. Jason.
So I don't have that fancy calculator, so I must substitution.
Oh, okay. Guess, does no one get it? Anyway, I'll try to answer for you. That's why I recommend getting it. 414.083 newtons, and my acceleration is 0.99973 meters per second squared. Yeah, there we go. And then, can you guys use the calculator? I'll show you guys quickly if you guys are not sure. Then of course the power required will be just be T1 times velocity. So what this essentially means, you can buy the calculator CNA anywhere. There's discussions or take a lot on Skype. It's really anyway. T1 is 414.083 times 0.9. It's nearly 1 basically. Oh, what am I doing? It's not times the velocity here, right? And the velocity was 1.8, sorry. So instantaneous velocity there will be 745. That's our final answer for that, yeah. Okay, guys. I'm leaving this to you now. So just be aware of how the bodies are accelerating or decelerating. that will change a few things. But you've got a ton of questions and examples for this. Make sure you attempt all the examples in the textbook. It's a good hint. And yeah, it should be around to keep the blood warm for now. I'll see you guys on Friday for a relative velocity, and make sure you prepare well for that. That's going to be a good one. So can be very tricky. Well, it's not actually. It will not lie. I'm gonna just explain it very well so you guys can understand. We're in and of early today, which is good. But it's fine. I'll see you guys Friday morning. For now, goodbye for now. I'll see you guys again. Cheers.